this is the point where we had left off in the last lecture, and we had looked at this group of order 4. Now, let me take another group of order 4. This particular group had 2 mirrors and a 2-fold rotation symmetry. Let us take a second group, which is just a 4-fold rotational symmetry, no mirrors. Now, if I list down the various operations of the 4-fold rotational symmetry, one is 2 pi or simply the identity, then 90-degree rotation, pi by 2, 180-degree rotation, pi, and then another additional 90-degree rotation will take me to a minus pi by 2. So, 3 pi by 2 will give me a counterclockwise rotation of 270 degrees. Equivalently, minus pi by 2 will take me clockwise 90 degrees, which is exactly the same operation, and this again is a group of order 4. Let me first geometrically visualize this group. So, I have a 4-fold rotational symmetry, and let me draw these dotted lines as just references. These are no symmetry elements, and in order to visualize this, I am going to use my asymmetric object. So, this is object number 1. This is taken through counterclockwise 90-degree rotation through position 2, then to position 3, and position 4, and another 90-degree rotation will bring it back to where I started from. So, let us make a group multiplication table for this. Putting the individual operations. And filling the first row, and the first column, so 1 a pi by 2 a pi a minus pi by 2. Now, let us see where I can put the identity operations other than the first cell that is already filled. If I look at a pi by 2, so I rotate by 90 degrees clockwise, follow it up with a minus pi by 2. So, counterclockwise 90 degrees, counterclockwise 90 degrees, that cancels the rotation, and hence this will produce the result of identity. Same thing I can look at a pi, a 180-degree rotation, follow it up with another 180-degree rotation, and that would again basically be a 360-degree rotation, making it an identity operation. A minus pi by 2, this time clockwise 90 degrees, follow it up with a pi by 2. So, in fact, so a pi by 2, follow it up with a minus pi by 2, follow it up with a pi by 2. So, this again results in identity, and rest of the elements let me just fill mechanically. So, here I cannot put a pi by 2 in this column. If I look at this particular column, I can only place I can fill a pi by 2 is out here, and what is left is a pi. Now, if I look at this second row, a pi by 2, a pi, what is left is a minus pi by 2. And then if I look at this column now, a pi, a minus pi by 2, 1, what is left is a pi by 2. And this way we can fill the rest. This is a pi by 2, and finally out here is a pi. So, our group multiplication table is filled. So, this was a little more bigger group than the previous one, but if I just go back to what we had done in the last lecture, I am just going a little ahead and then the logic will come later. This particular group is identified by the symbol 2. So, this is the group symbol. This group is identified by the symbol m. If I look at this particular group, I will call this group as 2mm, and the logic of this I will explain in a later lecture. Similarly, and you may have guessed that this group or this group is identified by the symbol 4. So, there is a certain logic to this symbols which will come later. Right now, I would like to take a little bit more elaborate example of a symmetry group, a point symmetry group. And one thing I should actually emphasize that these are all point groups, because there is one point in all of these groups, at least one point which is invariant. So, there is this point at A. Here in the group M, all the points on the mirror are of course invariant. Similarly, in the group 2mm, I have again one point in this two-dimensional group which is invariant, and similarly I have a group which is at the four-fold symmetry group point A, which is invariant. So, that is why they are called as point group. So, as I said, let us come to a more elaborate example. And let me take a geometrical shape to understand this example. Let us take an equilateral triangle and let us see what are the point symmetries associated with this equilateral triangle. So, very simply, there is a threefold rotational symmetry which is present in this equilateral triangle. Then we will also find that there are going to be 3 mirror planes passing through the center of the threefold rotational symmetry. So, one can designate that point. Again, there will be one point that will remain invariant. So, I can rotate this equilateral triangle through a threefold symmetry, which means 120-degree rotation, and the shape will come in self coincidence. Similarly, the reflection planes will bring the shape into self coincidence. So, let us also label these. So, this is, let us say, mirror M1, mirror M2 and mirror M3. So, therefore, subsequently there are going to be 3 symmetry operations, sigma 1, sigma 2 and sigma 3. And just for reference, so that we understand this symmetry through diagrams right now, that this vertex I have labeled as 1, this second vertex of the triangle I have labeled as 2 and the third one I have labeled as 3. Now, let me draw, suppose I can do 3 operations of the threefold rotation. Identity, that is doing nothing. Second, I can do 120-degree rotation plus 120-degree rotation, which means counterclockwise 120, or a minus 120-degree rotation, which is basically clockwise 120 degrees. So, if I do the operation of doing nothing, which is the identity, so obviously my vertices 1, 2 and 3 are in that same position. Let us do a 120 degree rotation. So, A 2 pi by 3. So, this is a 120 degree rotation. So, vertex 1 becomes this through after 120 degree rotation counterclockwise, this becomes 2, this becomes 3. Now, let us do minus 120 degrees, A minus 2 pi by 3. So, I am doing a 120 degree rotation clockwise. So, the position of the triangle now becomes, if I look at this, I am rotating it clockwise. So, 1 will come here, 3 will move here and 2 will move here. Now, let us do the 3 reflection operations. So, let us do reflection operation sigma 1 through mirror M 1. Now, when I do this, the vertex 3 which is on the mirror plane remains where it is, and 1 and 2 get flipped. So, 2 will come here, 1 will come here. Let us do the operation of sigma 2 through mirror plane 2. So, this time 1 will remain fixed, 2 and 3 will get flipped. So, this will become in this configuration. Third one, in this case this is sigma 3. What happens now? This is 3.2 remains fixed and 1 and 3 get flipped. So, the configuration would be like this. So, these are all the 6 operations that are there in this symmetry group. So, our group elements are 1 A 2 pi by 3, A minus 2 pi by 3, sigma 1, sigma 2 and sigma 3. So, this is a group of order 6. So, let us try to make the group multiplication table for this. And I will just write down all the elements. And the first thing I do is fill the top row and the first column. Now, let us again look at those operations which are inverses of each other. So, that when combined together the result would be the identity operation. So, if I consider a minus 2 pi by 3 and a 2 pi by 3. So, a minus 2 pi by 3, follow it up with a 2 pi by 3, this obviously will result in the identity and obviously also the reverse as well. So, therefore, this is identity, this one is identity. So, this is all that would be there for the rotations. Let us consider the reflections. Sigma 1 followed by sigma 1 we have already seen, the same mirror operating second time, identity, sigma 2 follow it up with sigma 2, identity, sigma 3 follow it up with sigma 3, identity. So, we have realized all the identity operations here, total there should be 6 and there are 6 out here. Now, consider the first or rather the first second row, first second column, a 2 pi by 3 follow it up with a 2 pi by 3. What would be the result of this? 120 degree rotation and another 120 degree rotation, which is nothing but basically 4 pi upon 3, and which as we have seen. So, this is 270 degree rotation counterclockwise, or it is simply a minus 2 pi by 3, 120 degree rotation clockwise. Hence, this would be a minus 2 pi by 3. Let us try to fill some more. Let us look at a 2 pi by 3, a 120 degree rotation clockwise, follow it up with reflection operation sigma 1. Let us come to the figures on the left here. So, this is my rotation after 120 degree counterclockwise. Now, in this I am applying the operation sigma 1. So, what will happen? 1 and 3 will get flipped, while 2 will remain where it is. So, instead of 2 3 1 it becomes 2 1 3. Let us look at where my 2 1 3 diagram is there, and you will see that here is my diagram which perfectly matches this, which means that this should be sigma 2. Now, in the rest of the column let me mechanically fill it. Sigma 2 is there, sigma 3 cannot come in the last cell of this second column. So, it has to come here. Now, if you look at this column, only one thing is left, which is sigma 1. So, sigma 1 comes here. Now, let me look at the second row, sigma 1 follow it up with, so a 2 pi by 3 followed by sigma 1, we got the result sigma 2. Now, let us look at the result of sigma 1 follow it up with a 2 pi by 3. What do I get? So, I am out here, this is where I have to fill sigma 1 follow it up with a 2 pi by 3. So, let us look at sigma 1. So, sigma 1, after a sigma 1 operation I have this triangle in the configuration 3 2 1. To this I apply a 120 degree rotation counterclockwise. So, this will become 1 3 2, and after 120 degree rotation it will become 1 3 2. Now, where is our 1, just a second, this is how did I get this? Okay, this is okay, 3 2 1, sigma 1 follow it up with a 2 pi by 3. So, this will become 1 3 2, and this is where we are 1 3 2. So, this should be sigma 3. So, hence this cell becomes sigma 3. Now, others I can quickly fill. You can also perhaps pause the video and think about how to fill the rest of the cells, but this way one can just go ahead and fill the rest of the stuff. So, one can realize in this that whenever two rotations are involved, there will be a rotation operation only, it cannot be anything else. If there are two mirrors involved, there will be a rotation. If there is a mirror and a rotation involved, there will be another mirror that should be there. So, with this in mind, we can fill the rest. A 2 pi by 3, sigma 2, sigma 3, sigma 1. Then I have out here, this is sigma 3, 1, A 2 pi by 3, A minus 2 pi by 3, and now rest it keeps becoming easier after that. Suppose I look at this particular column, I have minus 120, I have plus 120, I have 1, all I am left with, and I have sigma 3, all I am left with is sigma 1 and sigma 2. Now, sigma 1 cannot come in the last cell, because sigma 1 is already present in this last row. So, sigma 1 has to come here and sigma 2 has to come here. Similarly, let me just fill now the rest. A minus 2 pi by 3, there are two mirror operations, so it converts into a rotation. A 2 pi by 3, this one would be A minus 2 pi upon 3, and out here it would be A 2 pi upon 3. Now, one thing we can realize this, suppose I look at this particular which I did not fill, A 2 pi by sigma 1 followed by A 2 pi by 3, this was sigma 3. Now, realize this, that these two operations, when I change the order, they are not equal. So, this is a sign of that this is a non-abelian group, that is commutative property does not hold. Now, just before I conclude this lecture, let me geometrically, the way we have been using the asymmetric object to depict this group. So, I have a threefold rotational symmetry and I have three mirror planes. So, I have M1, M2, M3. So, let us start with my asymmetric motif 1, it is right handed. I rotate this by 120 degrees counterclockwise. This is 2, right handed, again another rotation of 120 degrees will bring me here. This is 3, right handed. Now, let the reflection operations work on this motif. So, I get a left handed, let me call this as 1 prime, left handed, this one 2 reflects to another left handed motif, call this 2 prime, left handed, the third one same thing, 3 prime and left handed. So, order of the group is 6, and you will also see that this order will also correspond to the number of asymmetric objects that are there. The number of asymmetric objects are also 6. Now, this particular group is assigned the symbol 3m. So, if I just quickly go back to my previous, we looked at a group 2, we looked at group m, we looked at group 2mm, looked at group 4 and we looked at the point group 3m. Now, in the next lecture, I am going to look at symmetry operations from the point of view of as matrix operations, and we can then make group multiplication tables using matrix multiplication. Thank you.